Okay, guys, so today we were going to go over some vector stuff. Um, basically an application problem of vectors, and it's going to be from another professor. And we were just going to go over it basically and like just walk through the steps he did and why he did it. So I'll just be explaining that. All right, so let's get started. All right. So here we have a problem that says an airplane has an airspeed of 500 kilometers per hour bearing north 45 east. So from the north, 45 degrees east. The wind velocity is 60 kilometers per hour in the direction of north 30 degrees west. Find the resultant vector representing the path of the plane relative to the ground. What is the ground speed of the plane and what is its direction? Okay, so three things, right? We just got to kind of find a picture that kind of shows how the vector is going to work. We're looking for the ground speed of the plane because we're having an airplane taking off and then the wind is also pushing against it. And then what is the ground speed? I'm sorry, what is its direction? So we're also going to find its north, its compass bearing. Okay. So let's go ahead and skip ahead a little bit. So here, professor wrote north and east. And as you saw here, it said we had an airspeed of 500 kilometers per hour. So that's the magnitude of the vector, 500. And then north, 45 degrees east. So from north went 45 degrees towards the east. Okay, it gave us that. And that's all he did in this step. And then here he did the wind velocity, or I guess, sorry, the wind vector. So we got north 30 degrees west. So from north went west 30 degrees. And then its magnitude was 60. So he hasn't written that yet. So let's check it out. There it is. So 60 degrees. All right. Let's keep going on a little bit. Okay, so here he gave us a picture of what the resultant vector is going to look like. So this bottom one here is the airplane vector. We're going to call it P, vector P in a second. And he put it here. And then we had the wind vector, and the way you show vectors being added is you take this one, place it here, and you take the second one, place it at the terminal point of the previous vector. And then from the initial point of the first vector, you draw it, and you'll see your new vector. Okay, let's keep going. Okay, he placed it here on the graph to kind of get a visual representation. Okay, so once again, ground speed and direction of the plane is what we're looking. So this vector here, that's what we're looking for. Okay, he labeled it, got 500, got 60. Keep going. Okay, so now he's labeling the vectors. Remember, we can use arrow brackets to denote vectors. So he's going to call this vector here its points. So from the initial and then the terminal point here, he's going to label that vector AB. And it looks like he's going to do the same thing for this vector, and he's going to call it CD. Okay, and if we're going to find the new vector, then we need to add these two. And the way we add those two is you take the horizontal component of both vectors and you add them. Then you do the same thing with the vertical components, B plus B. Okay, and then that's how we're going to kind of find the first step to finding the new direction of our vector. Okay, let's keep going. So he just redrew it and he labeled the vectors. So we call them this one P and this one W. And now we're going to focus on one vector and finding its points. Because remember, we were just given a degree and a magnitude. We have no idea what the horizontal and vertical component of this vector is. So what he has done is he has found the reference angle for this, and he labeled this x1 and y1, denoting your horizontal and vertical components of the vector. Okay, so here we have some math trying to find those actual components. So here's our reference angle, right? And if we're trying to find the x, we'll notice that's your adjacent, and we have the hypotenuse. Its magnitude is 500. So it's adjacent over hypotenuse gives me x over 500 is equal to cosine 45. So if I'm trying to solve for that horizontal component, multiply 500 to the other side, I guess both sides, excuse me, multiply 500 by both sides. You'll get 500 times cosine 45 is equal to your x1. And that's how you find it. It's just using SOHCAHTOA, right? In this case, we use the ka, adjacent over hypotenuse. It looks like he's going to do the same thing with sine. So let's see what he does. Same thing, except this time sine is opposite over hypotenuse. So we have y1, which is the opposite of this angle, and then the hypotenuse is 500. So it's over 500. Then he did the same thing multiplied by 500. And it looks like you can evaluate these values because they're special angles. So it's root 2 over 2, replaces that cosine 45. And then the same thing for sine 45. Okay, so let's see what happens. He multiplies it out and gets this value, 250 root 2 and 250 root 2 for y1. And this kind of makes sense because the 45-degree angle, at that point on the unit circle, you have the same value, and they're both positive. Okay? So let's go to the next one. Looks like he started drawing. Looks like we're going to start working with the second vector now, the wind vector, W. Let's keep going. Yeah, so we did the same setup, right? We had, so this requires some explaining. So remember, we went 30 degrees from north to the west, which means the reference angle here is 60 degrees. However, that is not our angle. Remember, we rotate from 0 degrees. So we rotated 120 degrees to get here. And that's the angle we're using, 120 degrees. Okay? So he used the same process. Cosine of 120 degrees is equal to x2 over the magnitude, which is 60, right? That was what it was. And so then he multiplied 60 over to the other side and got his x. It's the same process as over here that we did. Did the same thing for y. Found we can evaluate these values to be a negative 1/2 for the cosine and root 3 over 2 for the sine. Keep going. He solved out those values, got negative 30 for this, and then 30 root 3 for this one. So these are our two vectors now. Now remember, previously, we were looking to add these two vectors together to get our new vector. All right, so let's see what that looks like. It looks like this. Okay, so he took the two x components, added them together, got this value approximate. And then same thing here, got this approximate value. Okay, great. So we found the terminal point of the new vector. But remember, we still need the magnitude, and we also still need the actual direction in the compass, right? So we're not done just yet. I drew a new graph, get some things in here. So this is our new vector, the P plus W vector here. That's what he's drawing. Okay, so here we're trying to find the magnitude of the vector because that was in the problem that we were looking for. Remember, to find the magnitude of something, you just use the distance formula. In this case, since we're based at 0 for the initial point, we just square both the x and the y, and then we take a square root of it. Remember, it is x2 minus x1 plus y2 minus y1. Let me re-say that. It is x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay, in this case, the x1 is 0 and the y1 is also 0. So it's just these values. Let's find that. And the approximate ground speed of the airplane is this now. Remember, that's how we find magnitude. In this case, it's the airspeed. Okay, so let's keep going. And then, so now we are trying to find the direction this thing is going via compass, okay? And so to find that, well, we need a theta when it comes to our compass. And we have a vertical and horizontal component, which is why we want to use tangent, because we can use that y over x for tangent. So we plug these values in, take an inverse of it. Let's see what we get. we approximate theta to be this, 51.414 degrees, okay? Now keep in mind, because our vector is in quadrant 1, this is totally good. This is a good thing, okay? So we're set. So we're going to rotate 51.414 degrees. I'm sorry, let me restate that. So this is the theta that we're approximating, because remember, vertical component was this, horizontal component was this. So this is the theta we evaluated to be 51.414. But when it comes to the compass, remember, we start at north and then we move. So we have to find this angle here. To do that, all you do is take 90 degrees, which is this whole quadrant, subtract this from it, and it'll give you the complementary angle to it. Okay? And then, well, we started at north, and then we went this degrees east. So that's what he's going to finish it off with. Yep. And we were going what we found to be this from doing the magnitude. Okay. So this is an example of a vector application problem. Remember, there's a lot of graphing, showing how two vectors add to give you a new one. Remember, adding vectors is you take the horizontal components and add them together. You take the vertical components and add them together. We can use SOHCAHTOA to find those components. You want to use the magnitude equation, which is just a fancy distance formula, right? x2 minus x1 plus y2, x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And take the square root of it. That'll give you your magnitude for a vector. And then if you're dealing with the compass version here, you can use tangent theta to find that angle. All right, that is all I had for you guys today. Hope you have a good rest of your week. Hope to see you on Thursday.